So now that we have MTech installed, I would like to guide you through the first example. So you can find the example on this homepage under example 1. It's parent grain reconstruction and variant analysis in lath martensitic steel. And yeah, it actually follows the MTech example for martensite formation in steels, which is you can find in the documentation under phase transition and martensite grain reconstruction. So we're gonna run through the same data set and do kind of the same things, but using some of the functionalities of the ORTools toolbox. So you can see the example file right here. But yeah, what I would encourage you to do is to go to the ORTools main page, and then you just download the entire ORTools as a zip folder. And then you actually move the zip file to your favorite location. So mine is in MATLAB is right here. So our tools. What you want to do is you basically just want to open one of the examples. So this is the example one we're gonna deal with today. I'm gonna put those two next to each other so we can also see what happens in the command output. So this is the example file, and in theory you could just now click run and it will run all through the file and do the calculations, but this is really not how we've designed the toolbox to work. Like, it's better to run in sections or to run in advance. So you can click here to do run section, then it will only run this part here, and then afterwards this part and this part, and then you can see actually what each of these lines of code do. Of course, you can also do run advanced. This is usually what I do, which can also be abbreviated by Control, Shift, and Enter. So then it automatically jumps into the next box. So let's start in the first box here. So we do run advanced. And what we do is we basically clear the command window, close our figures, clear the variable space. Then we run this current folder function, which actually what it does is it adds all these folders to your MATLAB path. So most of the functions are sitting in the source folder, and for MATLAB to see them, we have to add them to the folder. So this is done automatically right here. And then we just initialize here our command window. So now next up, we're going to initialize MTech, and yeah, this consists of starting up MTech, and then you also want to set some of the settings like X direction, Z direction for plotting. This may be different for you. Then we're just going to find some default directories for where our data sits, where our ZIF files sit, the ebsd data, and the texture data. But this can also be adapted. So now we're actually going to load in the MTech's example dataset martensite, which is the one you also see on the homepage. You can always see down here that MATLAB is busy, and you see when it's done processing. Yeah, and since this is the first time I run this with this MTech, it has to download the data first, so that took a little longer. But now we can see the ebsd data is right here. So in the first part after that, we are going to calculate some grains within a threshold angle of 3 degrees. Then we're going to remove particularly small grains here with smaller than 4 pixels. And then after we've removed this data, we want to calculate the grains again. Just going to execute this. You can see it's busy. So when we're done with calculating the grains, we're also going to smooth the grains, which is going to basically smoothen out the grain boundaries a little bit. So yeah, this grain calculation usually takes a little bit of a while. In the meantime, I will tell you about the next block. So the next block is rename and recolor faces. So here you can actually put in some face names that you like. For example, gamma and alpha prime are the ones we use in this example. We could also do test face. And then when we run this block here, actually getting this window and be allowed to rename the faces, because by default, often from your ebsd dataset, you have like RMBCC old, which is not a nice face name to have in your figures. So we would like to rename this to alpha prime, which is the martensitic face. And iron FCC, we would like to rename this to gamma, which is the austenitic face. Then next, we actually open this function, which are all like ORTools functions, recolor face, where you can actually assign colors. So here it asks you, what should your martensitic face look like? You just choose one of your favorite colors. You can also go a little bit more advanced and go to this RGB blender. But yeah, I'm gonna use green for martensite, and then maybe dark red for austenite. So this block is finished. What do we have in the next block? So now we want to define actually our parent to child orientation relationship. So which is the parent phase, which is the child phase in this austenite lath martensite example. So let's just run this block. So we start with actually select the parent phase. So that would be gamma, select the child phase. That's alpha prime. So that's our martensitic phase. And maybe you just saw you can actually also load CIF files in if you actually don't have the phase. So if the phase is not part of the ebsd dataset, you can still load in the structural data of your parent or child phase from CIF files. I jumped over that a little bit fast. So in the beginning, we then assume a codium of Sachs orientation relationship, and after that, we use this calc parent to child command to refine the orientation relationship. So it will actually iteratively go through the microstructure, look at the misorientations between your child boundaries and child parent boundaries, and it will compare them. Okay, how well do they fit to the orientation relationship, and then iteratively kind of update the definition of the orientation relationship to match the microstructure more. So basically, you get an experimentally refined orientation relationship. So this has just been done, and after that, this command ORinfo, which is also a ORTools function, spits out information about the orientation relationship. So what's the parent phase? What's the child phase? Oh no, that was from earlier. So this is the OR misorientation angle. Then we have 110 is parallel to 100, and 111 is parallel to 011. Mind that you don't always exactly have the same planes that you would expect from Codimo Sachs or Nishiyama Wasserman here, because MTech cannot really distinguish between an FCC and the BCC phase or know what the interface looks like. Like usually you often have that the 111 plane in the parent phase or an austenite is parallel to the 110 plane in martensite. But for MTech, it can just well be the other way around because it doesn't really know which one is which. It only knows its cubic symmetries. Anyway, it doesn't really matter. The description is still very correct. So you get the rotation axis in parent crystal, parent coordinates and in child coordinates, and then you get the 24 variants and how they are misoriented with respect to each other. You can actually also see here how far the orientation relationship deviates from the next rational orientation relationship, which is defined by planes and directions. And we have around 2.4-degree misorientation here, which is kind of known that the experimental orientation relationship in Lath martensite deviates about that amount from coding of Sachs. So now we've actually refined our orientation relationship. So what we can now do, we can use some of the plotting functions in the ORTools toolbox. So I'm just gonna run these bit by bit so they don't all run together. So you can always mark a function and just use F9 to run that one. I'm gonna do that now. So we start with plot map phases. So this gives us a phase map. It's not very spectacular here because we have a fully martensitic microstructure, but you can see it actually adapted the colors that we assigned to the phase earlier. And you have the normal grain boundaries in black here. And you can adjust the line width right here. I recognize depending on your screen resolution, you might want to put this higher or lower. So the next thing is to plot inverse Pofegger maps of the parent and the child phase. This is nothing advanced, but it's quite important to actually be able to later on when we reconstruct the parent phase, compare whether this matches or not. So here we get a warning parent IPF X map empty, which just means, yeah, we don't have any parent phase in our ebsd data, but we are getting plot the child grain. So this is the Lath martensitic microstructure. Then we can do a child grain boundary misorientation map. The same also exists for parent child. I just didn't use this here because we don't have a parent phase, so that would just be an empty map. So we plot this, and what this does is actually shows us the misorientations that we have on our child boundaries. So this is here in degrees. And we can see that some of the boundaries look a little bit more colorful than others. And actually these are the prior austenite grain boundaries, because all the boundaries that satisfy the orientation relationship within the child's grains, they're actually red or blue. And this actually fits to, we see here that we have either very low misorientation, like 4 or 5 degrees, or something around 55 between the child grains. So that's actually reflected in here. Everything that's not in this range is probably already a high angle grain boundary between two parent grains. So now I think it gets interesting. We use this function plot GB misfit. And here I already set the command max color 5. That means that the color is basically thresholded at 5-degree misorientation. If you don't put this argument, it will just show you the entire range. I will show you in a second why this is interesting. So what we are actually plotting is the OR boundary disorientation. So that means how high is the disorientation between the misorientation of the grain boundaries with the misorientation defined by our orientation relationship. So basically, a low disorientation says that we have very good agreement with the orientation relationship, and the high disorientation means very bad agreement. And we can actually see that we have some boundaries here in dark red that have very bad agreement, and these are, of course, the prior austenite grain boundaries. And inside of these grains, we have like quite a good, quite low disorientation or quite good agreement. And yeah, by putting this color threshold to 5, it's very easily to highlight those prior austenite grain boundaries. If you don't do this, you will still be able to see everything, but it's not going to be as obvious. So then we have one more function, which is called plot map GB prop. And this actually is kind of the same plot, but just scaled a little bit differently. So what it does is it calculates the probability that the boundary belongs to the orientation relationship or not, and that's also done based on a disorientation. So here we just scale things from 0 to 1 and calculate the probability based on some threshold values. Let me just jump into this function. So you can always mark this function, to right click and then open, or you can do Control D instead. Oh yeah, somehow I plot this twice. So you can see here that you can also have the options of threshold and tolerance. If not, then these threshold and tolerance values are taken as defaults. So you can always change how this distribution here looks to change the kind of color coding of the probability. So anyway, these plots I think look quite nice, and they kind of already show you how well this orientation relationship applies to different parts of the microstructure. So after having done these plots, we can actually start with the reconstruction of the parent microstructure. So this is this block here, or this section. Again, I could do just Control Enter to run this whole thing, but I'm going to run it bit by bit here, just by marking and doing F9. Or alternatively, you can do right click and run, or evaluate selection. So we're gonna calculate a graph now. So this graph will actually look at all the child grains, so all the smart city grains, and see, okay, what are my neighbors, and basically make connector elements to all the neighboring elements. So this has been done. Then we do clusterization of the graph. So currently we have the Markov clustering implemented in MTech, which is a clustering algorithm that basically simulates a random walk in a microstructure. So all those connections between neighboring grains, they're basically showing paths in which direction an algorithm can walk by a random walk. But those connections, they're actually weighted by the disorientation from the orientation relationship. So this probability map here that you see here, everything that's black basically means there's a high penalty for the random walk to go in this direction, but there's a low penalty to go into the very light kind of, or like yellow-white kind of areas. So what that leads to is that by this kind of simulated random walk is that we actually cut off the boundaries that, or cut off the grains on boundaries that don't fit to the R that well, and we actually enforce the boundaries that fit very well. And by this, we actually cluster together the child grains that belong to one parent grain. So in this cluster graph in the future, one could also, let's say, introduce additional or other clustering algorithms. Right now, it's the Markov clustering that's implemented. So now we can actually calc the parent orientation from this graph. So now it will actually go through all these clusters and check out, okay, which orientations do we have, and then figure out, okay, how do these best, like if we calculate the parent orientation for each of these grains within the cluster, which one agrees best? And that's basically how the reconstruction is done. Mm. So this, of course, is a little bit of computational intensive. This will take a little longer. And yeah, usually this runs faster, but since I'm recording a video as well, my normal office laptop here is a little bit more under pressure. yeah, just to show what's going to happen next in the meantime. So as next point, we're gonna create a figure, and then we're gonna plot the parent grains and the mean orientation just to show how the reconstruction went. Um, just to be clear, all these kind of job dot points, they are part of MTag and not of the ORTools toolbox. So these are actually part of this new parent grain reconstruction classes. But we're of course using the same functions here to do the reconstruction. So now we can see actually that the parent grain reconstruction has been finished, and now we can run this last part here, which is making a figure and plotting the parent grains with their mean orientation. So now we can actually see that we have reconstructed parent grains. Like it looks very much as what we expected. That we have, yeah, quite spherical or polygonal kind of austenite grains. But we can also see that there's some small fragmented grains that might not be entirely correct. So what we can do, we actually get a fit with this reconstruction. So after the basic reconstruction of the whole cluster is done, the algorithm looks at how well does each of the individual alpha, prime, or martensite grains fit to this general austenite grains, considering the given OR. And some of these grains, of course, are not going to fit that well. Here we put a threshold at 5 to show you that there's some grains that are having more than 5 degree of a misorientation to the orientation relationship. So what we can do now, we can use this job revert command, and we can say that all the grains that have a fit that's worse than 5 degrees and all the grains that have a very small cluster size, smaller than 15, should be reverted because we're not very confident with the result. So after that, we can of course plot this parent grain, the parent grains again, and see what we have left. And we can see that now some of it has been removed, but in overall, let's say the picture looks a little bit cleaner, right? So as a next step, we now still have these empty kind of holes in the microstructure. And what we would like to do is to fill these holes with a different algorithm. So what we're going to do now is we're actually going to do calc. Use the command calc grain boundary votes. No C2C means that we only look at parent to child grain boundaries, because now we have the advantage that we already have a lot of parent microstructure. And now we could, for example, look at a grain like a martensite grain that's right here and say, hey, do you belong very well to this parent grain or that parent grain? How well do you fit? And then like this, we can basically let the microstructure grow into the voids. So after we've done the voting, we can actually evaluate this vote and calculate the parent microstructure from that. And this can be done iteratively, and you can also change the threshold for that iteratively. So we do this 5 times. We can see right here, we get a little bit of an output on what it's doing. And after this is done, we're going to plot the microstructure again. So this is how it looks now. We've filled up these areas, and I think it looks a lot cleaner than before. There's still some small areas that are not, let's say, filled, and we decide to keep it this way. I mean, you can always make the threshold even worse and force the reconstruction to do something there, but it just means within the, let's say, confidence interval with which we are with which we are comfortable, you cannot fill up these voids. So we just keep it that way. So as the next step, we can actually merge some grains that are very similar. So in orientation, you can put your own threshold here again, because we can see that now we have a lot of fragmented small child grains in here with kind of the same orientation. Sorry, reconstructed parent grains. And we can also merge inclusions. So if you have very small inclusions, even of a different orientation within a big grain, we can set a maximum size of inclusions that we want to absorb. So let's do this, and then in the end we plot the parent grain microstructure again, and we can see now we basically have the grains without all this small fragmentation. The cool thing is that in this kind of job object, which is like from the parent reconstruction class, we actually have all the connection between the new parent grains and the old child grains written as indices in there. So you can always kind of relate back, okay, what's the parent grain and to which child grains does it belong and how has it been merged? So everything is keeping track of. So now back to some ORTools functionalities. These were all like general MTech functionalities. So we have this function plot PDF variance, and this basically plots the variance of the orientation relationship in a pole figure of your choice. So by default does 0, 0, 1, but you can also put in your own pole figure selections. And all of these functions, just if I open this one, they have a lot of, let's say, additional options. You can change the color map as well. So it's always nice to have a look in here or in the documentation what you can do with these functions. So here we see the variance from 1 to 24, and yeah. So the next thing we're going to do is we're going to calculate the variance. This is an mtech function where it calculates the variance, and here it tells us the packet IDs are calculated assuming a 111 parent to 110 child planar relationship, or let's say interface. And this is kind of the standard for steels. You're also welcome to change this as an optional argument to this calc variance command. But yeah, it basically by default assumes this case of steels. So then we can use this ORTools function plot map variance to get a variant map. And on top of that, we plot the actually prior Austin grain boundaries. So we get this very nice plot. And again, if you're not a fan of the color scale, you can the color map, you can actually provide your own color map or a different default color map with it. And then we can also plot the packets. So the packets are here, and again we have the Austin boundaries around it. We have 4 different packets. Here we use a different color map because of aesthetic reasons, but yeah, you're free to use what you like with this. And all these figures you can just go and do a file, save as, and then you can either save the MATLAB figure, which will actually also contain the data, or you can use any kind of file format that you like if you want to use this figure for publication. So the last step, second last step, we're now going to reconstruct the parent ebsd data. So these are all grains that we've basically reconstructed with our clustering algorithm. But now from these grains, we can, knowing the parent orientation, the child orientation, the orientation relationship, we can actually also get back our original ebsd data just as parent ebsd data. So we're going to run this section, use this job.calc parent ebsd, which is again an mtech function, and then we're gonna just plot the parent ebsd. And here you see we basically now reconstructed the parent grain data, and all the unindexed points, most of them were unindexed to begin with. This has been a scratch to begin with, so it's also good to show that even though you might not have a perfect data set, the reconstruction works quite well. So now to the last feature, I have to give a little bit of warning here. If you run this function here, it will close all the other figures. So if you want to save something, do it now. So I'm going to run this. It's called grain click. What grain click does is it shows us now the parent grains here, and we can now click at any of these grains and get a lot of information about them. Sorry, there was a little problem there. It's a live demonstration, right? So when we run this grain click, we get this kind of map, and we can see the child boundaries in here, and then thick we see the parent boundaries, and you can now click at any of these grains to actually get some information on the mathematic transformation in those grains. So I click on this grain right here, and now actually the program is running in the background, creating a lot of different plots. I think in total we get 15 plots for this particular grain, and I'm gonna just briefly show you what those plots are all about. So now the plots are here. They actually just popped up on my other screen, so I'm just gonna drag them over piece by piece. So this one is of course the initial plot here, where we can now actually choose the next grain to continue if you want to. This is the parent orientation of the grain. Sorry, it's not the orientation. This is the parent phase. This is the child phase map. Then we have the parent grain inverse pole figure in x direction, and you can of course change this. Then we have the child orientations as an IPFX, so inverse pole figure. Then we have all the variants of that child grain. So here color code 1 to 24. Then we have a packet map where it shows us all the packets within this grain. Then we have a pole figure showing the mean grain, the mean grain orientation of the parent grain plus the actual orientation of the ebsd pixels in there. Then as the next thing, we actually have the theoretical positions of the child grains. So where the variants are going to be located for that particular parent grain. And then we have the same plotted experimentally. So these are actually experimental child variants that we found in our microstructure. Then we have the same for the packet IDs. So here it's the child grains in a pole figure with packet IDs. Then we can plot the same thing as an inverse pole figure. So these are the different variants in inverse pole figure notation. These are the packets in inverse pole figure notation. So now we get a histogram here of how frequent the variant is in this kind of in this grain. Let me just see if I can find the map again. So here it tells us that number 5 is quite frequent. And we can see 5 is basically this super large grain here. And this is basically an area normalized frequency. So it actually looks at the area fraction of each variant, which I think is the most relevant. Then the same thing happens here for the packets. So we can see that packet number 4 is quite frequent. And we can see, of course, that this is true. So yeah, these are all the plots you can get from grain click, and you can now start clicking at the next grain, and then it will pop up with the next plots. But you can also see here, right click to exit this kind of grain click functionality. But beware, it will close all your figures as well. So yeah, this grain click is basically the last part I want to show you for today for the ORTools toolbox. And yeah, I hope you enjoyed the functionality of the toolbox. I think it can make pretty simple and pretty good plots for analyzing multi-static transformations. Have fun.